Now a very quick and short summary of equations of ellipses and hyperbolas, which are centered at the origin. Okay? So if you have x squared over a squared plus y over b squared equals 1, that gives you an ellipse. It has two foci in case you need to work on those, c0 and negative c0, where c is the square root of the absolute value of a squared minus b squared. Okay? Assuming a is greater than b. If b is greater than a, well, your foci would then be at 0, c on the y-axis, 0, negative c. Okay? You graph this ellipse, and this is a picture where a is bigger than b. You graph this ellipse within the rectangle I've shown here, where the rectangle is centered here. This distance is a, this distance is a. This distance is b, this distance is b. And then the ellipse just fits inside there. Here are the two foci. And the foci have the characteristic that the sum of these two distances, focus to a point on the ellipse to the other focus, is the same no matter what point on the ellipse you choose. So if I chose this point on the ellipse, these two distances would add up to the same thing as these two distances. Okay? That's a very quick summary of the major, of the simplest properties of an ellipse. Now you have to rearrange an equation to get into this form, but that's generally easy to do if the equation really does give you an ellipse, and we'll see how that works. Okay, hyperbola, very similar to this, except one of these terms is going to have a minus on it, the other is going to have a plus. Now, if the x term has a plus and the y term has a minus, you again draw the same rectangle. A units here, A units here, B units here, B units here. And you do draw, in this case, the diagonals and extend those diagonals, because your hyperbola is going to be asymptotic to those diagonals, wherever it happens to be. Now, if the x squared term is positive, the y squared term is negative in this form, your hyperbola is going to be here, the orange hyperbola, corresponding to the orange circles I've got around the plus and the minus sign. Okay? The vertex will be here, just like you have a vertex for the ellipse, but the hyperbola opens this way. It looks something like a parabola, but it's not a parabola, because if it was a parabola, the slope would keep changing and would approach horizontal as x goes to infinity. In this case, the slope approaches that of this line, and in fact the hyperbola is going to be asymptotic to this line and to this line. Now, I didn't draw that really well, but you get the idea. Okay? And I know that this thing intercepts the positive x-axis, because if y is 0, you can solve for x. You have x squared over a squared equals 1, x squared equals a squared, x equals plus or minus a. If x was equal to 0, you'd have no solution, because you'd have a minus on your y squared over b squared. Y squared is positive, so is b squared, so this term is negative, and it can't equal 1, which is positive. So if x is 0, you get no intercept, so you don't have any point on the y-axis that corresponds to this orange hyperbola. Okay? On the other hand, if this term is negative and this term is positive, the reverse is true. If y is 0, you don't get an x. Well, y is 0 on the x-axis, so you don't have an x-intercept. You have y-intercepts. You need to understand that. But that's how you draw the parabola. And you're going to need to do this because we're going to be talking about quadric surfaces, which I'll talk about here in just a second. Okay. Now, a parabola has an equation like y plus ax squared equals b, or x plus ay squared equals b. I'm not going to talk about that. This is just a multiple of y equals x squared, okay? And maybe shifted up or down, shifted right or left. So you should understand the equations of parabolas completely well, even if you haven't done conic sections. And if you don't understand them well, you'll read about it. It's a little simpler than the picture for the conic section. Now in general, sorry, I had to step away and check the time because I've got a class in 9 minutes, but we'll get done by then. In general, any equation of this form in x, y, z is what we call a quadric, well, the graph of this sort of a equation or a function, well, an equation, is what we call a quadric surface. Okay? A quadric surface has a property that you have all possible combinations of x, y, and z with multiples of degree 2 or less. Degree 2, that's like x squared, y squared, z squared. So the simplest quadric surfaces just have some multiple of x squared, some multiple of y squared, some multiple of z squared, and a constant. So I've got those in white. So if you eliminate the orange and the green, you have the simplest possible quadric surface, which is centered at the origin, which has a lot of symmetry about the origin. Okay? And now, if you add an x, a y, and a z term, and it looks like I added an x, a y, and a y term. Again, I was making the mistake of thinking at the same time I was writing and talking. Then you have a surface whose center is not necessarily the origin. If D, E, and G are all if any of these are non-zero, then your point of symmetry is not the origin. Okay? And then you have to complete the square on your x terms, and on your y terms, and on your z terms to figure out where the axis of symmetry is. And of course, when you complete the square, you're also going to get constant terms, and that's going to change the value of the n term. And that's very easy to do if you know how to complete the square. You just get surface, well, I'm not going to talk about it right now. It gets much more complicated, or significantly more complicated, if you also have x, y, xz, and yz terms. These also have degree 2. You got the product of 2 of your variables. That makes it degree 2. So these are degree 2 terms that cause the whole thing to have to rotate in space. And we might or might not talk a lot about that, depending on how much time it appears that we have and what we need to spend our time on. Okay, so just taking now the simplest case, just the terms in white with no need to complete squares. Let's just look at this surface. Okay, now take a look at that in the next video, but you give it a little thought and answer the question, what would this surface be if z was equal to 0? Well, of course, then this term would go off and we'd have something times x squared plus something times y squared equals 3600. Well, it turns out we'll be able to put that in the form of an ellipse. If y is equal to 0, then we're in the xz plane, and we have a hyperbola because we've got a negative sign here. So we'll talk about that in a little bit of detail in the next video.